KT 221 Digital Electronics 2. Chapter 3, Memory Basics. Today's outline: Memory Basics, Memory Definitions, Memory Organizations. RAM, Static RAM, SRAM. Memory Definitions. Collection of cells capable of storing binary information. Contains electronic circuits for storing and retrieve information. Used to provide temporary or permanent storage capability. Memory basic process. Info/content from memory is sent to HW, usually consist of registers and combinational logic, to be processed. The processed info is then returned to the same or different memory address. Input and output devices may also interact with memory. Memory. Hardware. 4. Processing. I/O. Printers. Mouse. Keyboard. Monitor. Digital camera. Scanners. Plotters. Thumb drive. External memory. Types of memories: random access memory, RAM. Write operation, stores new info. Read operation, transfer the stored info out of memory. Read-only memory, ROM. Perform read operation only. Memory data elements. Typical data elements are: bit, a single binary digit. Byte, a collection of 8 bits accessed together. Word, a collection of binary bits whose size is a typical unit of access for the memory. For example, 1 byte, 2 bytes, 4 bytes, 8 bytes, etc. Memory data: a bit or a collection of bits to be stored into or accessed from memory cells. Memory operations: operations on memory data supported by the memory unit. Typically, read and write operations over some data element, bit, byte, word, etc. Memory organization. Organized as an indexed array of words. Value of the index for each word is the memory address. Often organized to fit the needs of a particular computer architecture. Some historically significant computer architectures and their associated memory organization. Digital Equipment Corporation PDP-8, DEC Alpha. Used a 12-bit address to address 4096 12-bit words. IBM 360. Used a 24-bit address to address 16,777,216 8-bit bytes, or 4,194,304 to 32-bit words. Intel 8080, 8-bit predecessor to the 8086 and the current Intel processors. Used a 16-bit address to address 65,536 8-bit bytes. Memory block diagram: a basic memory system is shown here. K address lines are decoded to address 2 meters words of memory. Each word is n bits. Read and write are single control lines defining the simplest of memory operations. K address line. M. 2 meters words. N bits per word. Refer to next slide for example. Memory organization: example of memory contents above. K address line. M. 2 meters words. N bits per word. Example of memory contents above. Address bits equals 3, M equals 3. Data bits equals 8, N equals 8. Therefore number of address lines equals K equals 2 meters, 23 equals 8. Address range equals 0 to 2 meters minus 1, therefore 0 to 23 to 1, address range equals 0 to 7. One word is the size of the memory content, so the memory above has 8 words of 8-bit data. Memory organization: example, address bits equals M equals 10. Data bits equals 16, N equals 16. Address line equals 2 meters. 210 equals 1024 or 1K, labeled 0 to 1023. memory content equals 16-bit. So the memory has 1K words of 16-bit data or 1K x 16-bit memory. Note: K, kilo, equals 210. M, mega, equals 220. G, giga, equals 230. Other example: 64K equals 216 equals 26 times 210. 2M equals 221 equals 21 times 220. 4G equals 232 equals 22 times 230. What is the address bits, M? Memory operations require the following: data, address. An operation. Typical operations are read and write, RAM. Read memory, an operation that reads a data value stored in memory, takes from memory. Place a valid address on the address lines. Activate the read input. Note: the content of the selected word are not changed by reading them. Write memory, an operation that writes a data value to memory. Apply data on the data lines. Activate the write input. Other than read/write, RW, chip select is used to enable a particular RAM. It is sometimes called memory enable. Memory enable. RAM integrated circuit. Types of random access memory, RAM. Static, information stored in latches. Dynamic, information stored as electrical charges on capacitors. Charge leaks off. Periodic refresh of charge required. Dependence on power supply. Volatile, loses stored information when power turned off. Example, FPGA-Flex 10K. Non-volatile, retains information when power turned off. Example, CPLD, Max. RAM, cellarize and coincident selection. Memory arrays can be very large equals greater than. Large decoders. Large fanouts for the bit lines. However, the decoder size and fanouts can be reduced by using a coincident selection in a two-dimensional array. Uses two decoders, one for words and one for bits. Word select becomes row select. Bit select becomes column select. Example, coincident selection 16 by 1 RAM chip. 16 equals 24 equals 4-bit add. A3 A0. The column decoder is enabled with the CS input. When CS equals 0, column decoder is disabled and all OP are 0 and none of the cells are selected. A3 and A2 used for row select. A1 and A0 for column select. Figure 9.7. Morris-Mano, page 410. Example, coincident selection. If address is 1001, A3, A2 equals 10, row decoder line 2 active. Activating RAM 8, 9, 10 and 11. A1, A0 equals 01, column decoder line 1 active. Activating RAM 1, 5, 9, 13. The intersect RAM is RAM 9 is activated. Other RAM cells not selected are disabled. Then it depends on the operation functions, read or write. Read, data out through OR gate and tri-state buffer. Write, data available on the data input line is transferred into the selected RAM cell. Figure 9.7. Morris-Mano, page 410. Constructing RAM. Previously, block diagram of a 16 by 1 RAM using 4 by 4 RAM cell array. How to create 8 by 2 RAM using 4 by 4 RAM cell array. Number of address bits equals 8 equals 23 equals 3 bits. Number of data bits equals 2 bits. 3 bits addressing. 2 bits at row decoder. 1 bit at column decoder. Since 2 bits at a time are to be written or read. 2 input lines. Data input 0. Data input 1. 2 output lines. Data output 0. Data output 1. Example. If address is equals 011. Row decoder equals line 1. RAM equals 4, 5, 6 and 7. Column decoder equals line 1. RAM equals 2, 6, 10, 14 and 3, 7, 11, 15. Therefore, cells 6 and 7 are activated. Figure 9.8, Morris-Mano, page 411. Constructing RAM. How about 32K x 8-bit? Address bit equals 32 by 210 equals 25 by 210 equals 15 bits. Data bit equals 8-bit. Without coincident selection, a single decoder would have 15 inputs and 32,768 outputs. 32 by 1K equals 32 by 1024. And 32,800 No of gates. With coincident selection, make row and column equal. Total RAM equals 32K x 8 equals 256K equals 262,144. Take square root of 262,144 equals 512. 512 equals 29, meaning 9 bits is fed to the row decoder. Remaining 6 bits is fed to the column decoder. Row decoder equals 9 to 512 line decoder. Column decoder equals 6 to 64 line decoder. No of gates equals 608. Array of SRAM ICs. If an application is larger than the capacity of one chip, then there is a need to combine a number of chips in an array to form a required size of memory. Depends on two parameters. No of words. No of bits per word. Number of words equals address line. 1 bit added to address bit would double the no of words. Number of bit equals data input and output. 1 bit added to the word size, 1 data input and output must be added. Example, memory chip. How to construct a 256K x 8 RAM using this 64K x 8 RAM chip. No of words is the same. No of address is not the same. 64K 256K. 64K equals 26 by 210 equals 16-bit address bit. 256 equals 28 by 210 equals 18-bit address bit. An additional 2-bit is needed for the address bit. Constructing 256K x 8 RAM using 464K x 8 RAM chip. 2 additional address bit is applied to a 2x4 decoder and represent the MSB of the address bit. How many 64K x 8 RAM chip to add? Additional 2-bit equals 22 equals 4 of 64 by 8 RAM. Use memory enable to activate the decoder. Constructing 256K x 8 RAM using 64K x 8 RAM chip. When bit 17 and 16 equals 00, the first 64 by 8 RAM is activated. Address 0 to 65,535. When bit 17 and 16 equals 01, the second 64 by 8 RAM is activated. Address 65,536 to 131,071. When bit 17 and 16 equals 10, the third 64 by 8 RAM is activated. Address 131,071 to 196,607. When bit 17 and 16 equals 11, the fourth 64 by 8 RAM is activated. Address 196,608 to 262,143. Figure 9.10, Morris-Mano, page 413. What is we are to expand the word size? Example, 64K x 16 using 64K x 8 chip. No of chip to be used refers to the word size. In this case, 16-bit is to be constructed from 8-bit words. Therefore 2 of 64kx8 chip is to be used. Connections. Address line is input to both chips. CS is common to both chips. RW control input is also common to both chips. Input and output data line is split. Constructing a 64kx16 using 64kx8 chip. DIN 15.8 DIN 7.0 DOUT 15.8 DOUT 7.0 Exercise. How many 128kx16 RAM chips are needed to provide a memory capacity of 1 MB? How many bits of address lines are required to access 1 MB? How many of these lines are connected to the address inputs of all chips? How many lines must be decoded to produce the chip select inputs? Specify the size of the decoder.